basically, the information that you just, calculated is giving you kind of the effectiveness of the separation. So we started to see the red pull out at 1 milliliter, and the center of the bandwidth was about 1.4. This was the center of the bandwidth. So if I can do a good job here at drawing, we could say that maybe that first hump looked like this, and this was the red. And you can look in your lab book, right? The center of the bandwidth was about 1.4 milliliters for the red. And the blue, it looks like it started at about 2.2, so maybe about right here. And the center of the blue was at about 3.2, right? Center was right here. So this is a much broader bandwidth. And so this will be like, much broader right here. And there's your blue. So can we say with a certain amount of degree of certainty that we were effectively separating these two dyes? Do you guys see how there's a blank spot right here? That's good. That means that we had an effective separation. All right, so let's go on to part C. So in part C, they want you to calculate something called the capacity factor. The capacity factor is just basically a number that represents how attracted the dye is for that set pack material. This is kind of like a way to measure the overall polarity of the dye. The higher the value, the more non-polar it is because it can be stuck inside of the set pack. The lower the value is, that means it's more polar and it wants to push through first. So I think you can already tell from the data that red came out first, right? So we're expecting our red dye to have a low capacity value, and we're expecting the blue dye to have a very high capacity value. They gave you this really groovy formula, all right? Basically what we did is we're gonna take the center of the band where most of the dye was coming out, right, from part B. We're gonna take those values, and we are gonna subtract the volume of the actual set pack from it, and then divide that again by the volume of the set pack. All right, I know it sounds a bit confusing, but let me just help you out with the red dye part. Okay, so the red dye, we had the center of the band happening at 1.4 milliliters. This is where most of the dye was coming out. We are going to subtract the volume of the set pack, which they gave to you. They said that the volume is 0.49 milliliters, but if you look at the sig fig here, you see how this guy only has 1 decimal. The value is 0.49. If you want to just kind of round that to just 1 decimal, you can. So I'm going to go like this, milliliters. And you divide that by the 0.5 milliliters here. And so the red dye has a retention value of 1.8 milliliters. Now, if you do that for the blue, all right, I'll give you some help here. Let's see, check your work. The center of the band was at 3.2 milliliters. Again, subtract the volume of the set pack and divide again by the volume of the set pack. The blue dye's retention value is 5.4 milliliters. So it seems like the blue dye is attracted to the material inside of the set pack. That means that the blue dye must be a little bit more non-polar than the red dye, because red dye came out first and the blue dye came out second. In part D, they're looking for something called a selectivity separation factor. They symbolize it as alpha. Hey guys, seriously, all this value is an indication of whether or not you had a good separation between the two dyes. We want the value to be between 2 and 10 to indicate a good separation. So if you have a value that is less than 2, you had poor separation, very poor. And the way that they do this is they want you to put those, do you guys remember those retention values? We want to put those retention values into the form of a fraction. And you always put the larger value on top. We don't have any separation factors that are less than the value of 1, okay? So we're going to put that larger factor. Look back at part C. The blue dye had a factor of 5.4, and the red had a factor of 1.8. All right, and this gives you a separation factor, or selectivity separation factor of 3.0. That means you had a pretty good effective separation. In part E, they want you to calculate something called the resolution. This is a measure of how well the two dyes are separated by the column. How effective was the column at separating out the dyes. And they give you a pretty groovy little formula. Don't want you to worry too much about it. Let's check it out, okay? What you have to do is you have to take the center of your band, which we calculated in part B, take the center of the band and subtract the two values. Then you have to divide by the overall wavelength of each of the dyes and take those, add them up, and like halve them. You got to put them in the middle and halve them. All right, so let me just kind of show you how to do this. So again, this is resolution. They symbolize it as R. On the numerator, let's take the center of the bands that you calculated in part B. All right, the blue had a value of 3.2. The red had a value of 1.4. Okay, those are milliliters. And then on the bottom, we're going to take half, see how I'm doing the 0.5, and we are going to add the wavelength of the two. This goes way back to part A, okay? We're going to take half of the 1.9, that was the blue wavelength. Remember, it was a really fat wavelength. And let's add that to the wavelength of the red, just like that. You should get a value of 1.3. So what does a value of 1.3 actually mean to you? The numerator is basically the volume between the band centers, right? And the denominator represents the average bandwidth, okay? The greater the selectivity, the value here, the larger the numerator is going to get. And therefore, the greater the resolution. You're looking for this value to be larger than 1. The more larger it is, the more effective you were at separating. All right, everyone. I really hope this has helped you out quite a bit. So please take this lab as just understanding that we're trying to effectively separate solutions, and all of this data stuff that you just did is a measurement of the effectiveness of the separation. I hope this has helped. Bye, guys.